I'm Tian Feng, a PhD student from Singapore University of Technology and Design. It's a great honor for me to be here. Very first time to presenting my work, crowd-driven mid-scale layout design, with Professor Craig Lafayette from UMass Boston. We propose an approach to automatically synthesize mid-scale layouts with respect to human factors. Let me begin my talk by motivating our work. We were motivated by the problem of layout design. Conventional methods are focusing on either large-scale problem like urban planning or small-scale problem like residential design. Successful products like S3 City Engine and Autodesk Home Styler were hence proposed and are indeed helping people. However, we noticed the design of social places with many visitors traveling had been less studied, like malls and train station terminals. We term such type of layouts mid-scale layouts. So researchers are always making efforts to turn the solution to this architecture-related problem automatic. Among all architecture design factors, the human factor is critically important, for human activities and architectures are highly coupled. This point of view has also been supported by some master architects. In fact, it is not difficult to find examples with or without consideration of human factor. For even worse examples, recall what we have experienced during the reception at Monday night. Is that? So our goal is to put human factors back into the layout design and synthesize crowd-aware mid-scale layouts. But how can we embed human factors into the process? I think for us people in computer graphics, the solution seems straightforward: crowd simulation. Okay, next I will have a brief pass on related work. Urban layout modeling has been a hot topic since procedural modeling of cities proposed in SIGGRAPH 2001. After that, procedural modeling has been a mainstream method to tackle the problem. However, it requires expertise in designing rules and tuning parameters values. In order to solve those issues, a forward procedural modeling, amazing works applied inverse procedural modeling to make urban models satisfy user-given indicators. Meanwhile, some researchers switched to example-based approaches. However, sometimes the outputs may look identical to corresponding input real-world data. Recently, global optimization is becoming a new choice, and it makes output layouts converge to certain metrics. In comparison, residential problem seems easier to solve. Traditional approaches focused on exhaustively searching for possible design solutions over a certain number of rooms. And connectivity relationships were also utilized. And nowadays, researchers are applying data-driven optimization, which shows good performance. Crowd simulation has been used widely for analysis and evaluation in urban and architectural domains. Agent-based simulation is well known for its capability of capturing individual behaviors, however, asking for huge computation. In comparison, continuum model describes the motion of many objects with aggregated behavior, at the same time maximizes efficiency. It is noticed that some hybrid solutions have been proposed based on both mentioned strategies. Okay, next we go through our approach in detail. Here is the overview of our approach. We designed the layout in an optimization style. Our optimizer takes as input the mid-scale domain, which is the area within a boundary, and outputs crowd-aware layouts. It is done by optimization against agent-based costs from crowd simulation and the prior cost from user-given target values. The layout is iteratively updated until it converges. Ideally, the agent-based cost should be computed directly by performing an agent-based simulation iteratively. However, it would take hours to finish the huge computation. Hence, we approximate the agent-based cost by supervised learning that boosts optimization with acceptable accuracy. Let me start by representing layouts. Obviously, a layout compromises a number of sites, like stores, facilities, services, that can be accessed by a set of paths. Then, we represent the layout as a graph. Each side door, layout entrance, and a path intersection is taken as a node, and each path is regarded as an edge. With a graph, we need to think about how agents travel inside in the simulation. Agents represent human visitors in the layout. We here define a simple agent-based simulation model that focuses on movement, perception of crowding, and locomotion. Need to explain that our approach also works with other crowd simulation models. I will show some results later. The table here depicts some of our agent's properties. An agent will enter the layout at a certain time point and finish his or her trip after a certain time length. It is also given a visit sequence that indicates which types of sites to visit. The agent's walking speed will never exceed a certain value, which we call default walking speed. And the agent's walking speed will be affected by the perceived crowd density within a certain social distance. Let me explain this in detail. So, according to the social distance theory, a person may start to feel uncomfortable or crowded if there are any other people than his or herself within a certain distance, which we call social distance. The crowd density perceived within a social distance will affect a person's walking speed in a negative manner. Specifically, in our approach, each agent takes a perceivable space, that is the intersection of current paths and agent's social distance circle. The perceived crowd density is the number of other agents over its perceivable space. The agent's walking speed will be lowered when the perceived crowd density is over a baseline density. This is from the previous definition. Obviously, higher the crowd density, lower the agent's walking speed. But it will never be lower than a lower bound value to prevent total stuck. Having the agent model, we run a simulation by controlling every agent with a simplified state machine. After entering the layout, the agent repeats the process. Think of the next target site, walk to the target site along the shortest path, and visit the target site for a time-specific period, which could be like learned from statistics. After all sites in the visit sequence are visited, the agent leaves the layout. The agent's speed and location will be updated after every time interval in the simulation. And the simulation ends when all agents have left. This is all about our agent-based simulation model. Let's move on to the optimization phase from the cost function. The total cost function is a weighted sum of two sets of cost terms. The prior costs are from comparing intermediate layout values to user-given target values, encodes the user's requirements. We consider three prior target values here: target total number of sites, target number of sites in each type, and a target floor area ratio, which is from architectural domain. The agent-based costs are from the simulation. Let me introduce the agent-based costs in detail. The mobility cost term tells how smoothly agents walk in an agent. It is calculated by comparing the real-time walking speed and the default walking speed of the agent. High cost here means that the agent may walk slower than expected. The accessibility cost term here tells how reasonably the sites are distributed in the layout. It is calculated by normalizing the sums of walking distance between each pair of two consequent sites. High cost here means that agent may usually walk longer to find next target site. The coziness cost term tells how comfortable agents feel when they are visiting sites. It is calculated from the real-time average crowd density of the site which agent is visiting. High cost here means the agent may usually feel either too crowded or too empty when visiting the sites. Actually, this is from some study in consumer psychology. The total cost is a weighted sum of agent-based cost terms and prior cost term. As I mentioned, to efficiently explore the solution space, we applied simulated annealing technique to the optimization. At the beginning, we set a high temperature to allow the sampler to more aggressively explore the solution space. Over iterations, the temperature is gradually decreased. Near the end, the temperature drops to 0, which hardly allows sampler to refine the solution. We applied MCMC here to synthesize layouts in an optimization style, seeking for layouts with global minimum cost. In each iteration, a move is proposed, which can be either accepted or rejected by a transition probability. If move is accepted, the layout is modified accordingly. If rejected, it stays the same. We have some moves here, like we can slide the boundaries of two sites, we can change the width of a path, we can change the type of a site, or we can add a new path there or remove an existing path. Note here we can able to add both like straight line-like or curve-like paths. Or we can merge two sites into one or split one into two. Or we can swap the site distribution of two blocks. Theoretically, we may finalize our approach here, but during our earlier experiments, we found the optimization process with cross-simulation could be very time-consuming. This is because cross-simulation needs running in every iteration, while the optimization usually consists of hundreds of steps. Inspired by the ideas of previous data-driven approaches, we managed to think of using supervised learning to approximate agent-based costs. Specifically, we look for the relationship between the layout features and agent-based costs, and hence approximate costs using nonlinear regressors trained by data from real-world layouts. This makes the computation of costs scalable and independent regarding the number of agents. The features we use for training regressors may be classified into three categories. Like for geometry features, they're focusing on shape, like width of path, length of path, area of site, or area of the whole layout. For topological features, they are focusing on network, like the travel convenience, some centralities like the node valence, closeness, and betweenness. For general features, we may have something like histogram of sites of different types, number of agents, or simulated hours. Note here we may use some like simple statistics values as actual feature values. We have found and digitized 80 real-world layouts under 4 mid-scale scenarios from different countries using SIGGRAPH. For each layout, we run agent-based simulation using 3 different numbers of agents for 2 different numbers of simulated hours. Altogether, we have 6 combinations of settings for each layout, giving us 480 training samples in total. For each training sample, we extracted its corresponding layout features and computed agent-based cost to train our regressors. The trained regressors have shown pretty high accuracy, sometimes even higher than like 90% when approximating costs given test layout features. Here we show some layout synthesized by optimizing with both cross-simulation and regressors-based approximation. They look visually like similar, but however took diverse time usage. Ones with cross-simulation cost on average over 4 hours, while those with approximation only ask for less than 5 minutes. Next, we show some of our results. We have synthesized layouts for 4 scenarios: mall, train station, building, theme park, and campus. The original layouts are real-world layouts in North America and Asia. We set a different number of agents to different scenarios. Here, we also applied other 2 cross-simulation models, continuum cross and path sim, for computing agent-based costs in our approach. The synthesized layouts are on the right 2 columns, which are similar to layouts synthesized with our own simulated model regarding both visual appearance and like the later evaluation. We found something interesting here. For Mall 1, our synthesis is with more facilities like washroom information counter in blue color. In addition, some shortcuts are created for easy access. For Mall 2, our synthesis is with like wider paths and more reasonably distributed sites, especially for those electronics and IT stores in green color. Okay, here are the synthesis for other 3 scenarios: train station building, theme park, and campus. For train station building, our synthesis is with the ticket office as a layout center, where it's easily accessed from all corners inside the layout, while the real-world ticket office is located at a corner without shortcut to the center area, and this leads to crowdedness at peak hours. From our synthesized 2D layout, realistic 3D scene could be produced for various purposes. This is one example. In addition, we have evaluated synthesized layouts by 2 third-party cross-simulation software, AnyLogic and Pathfinder. Regarding the common metric of these two software, average crowd density, the real-world layouts show higher possibility of causing crowdedness than our synthesis do. Okay, this is with AnyLogic. And this is with Pathfinder. The evaluation results are similar. We have also invited a group of senior undergraduate students in architectural design to use our approaches. They gave us some positive comments. Here are some user syntheses. This is for Module 1. And this is for Module 2. User syntheses were also evaluated by AnyLogic and Pathfinder. They are good in terms of the average crowd density. So please refer to our supplementary document for more details. Next, I will finish my presentation by summarizing our work. So we focused on the problem of mid-scale layout design, which was less studied before. And we proposed an automatic approach driven by cross-simulation, especially agent-based cross-simulation. And we boosted the computations of agent-based costs by nonlinear regression instead of running full simulation. And we also demonstrate the practical value of our approach for different mid-scale scenarios. So in the future, we may bring more commercial factors to our problem to make the layout gain more profits and benefit from anchor stores. Besides, the synthesized layouts need work well in emergency evacuation regarding safety concerns. It is also draws our attention that some interesting patterns are there, like clustering of similar sites. I know all of you could see a clustering of cosmetics booths in department stores or in malls. Last but not least, we want to investigate the layout design regarding some complicated relationships among aesthetics, consumer psychology, and sociology. Okay, this is the end of my presentation. Thanks for listening, and now I'm very pleased to answer questions.
Thank you. We have time for 2 questions, if they're short.
Hey, this was a really cool paper, but I feel like sometimes malls are designed to force you to walk around so that you see all the other stores. Mm-hmm. So I'm not that surprised that your designs ended up being more efficient, because I think that's not always the goal. So I was wondering if you had any thoughts on how you might incorporate that kind of consideration.
Yes, that is not the only consideration for us. Yes, a good more design to need take concerns of crowd factors, and as I mentioned in the very beginning of the slides, it is highly coupled with architectural design. If it is not concerning human factors, I think it will lead to a very very unsatisfactory visitor experience.
I have a question.
Hey.
You mentioned that you looked at different programs like theme parks and malls. Did you use different parameters for each of those? And if so, how did you derive those parameters?
You mean parameters for simulation or for design? The whole design,
I guess, yeah.
I mean that because I mentioned that we use some prior costs. These prior costs actually are calculated by comparing some user-given target values. So these are from some user-given requirements. So by using these prior costs, we can to make the layouts to a similar style that the user expected.
So do you think it's generalizable to other programs like office layouts and?
Yes, I think so.
Thank you.
Thank you.
I want to add a question.
Okay.
Could you explain how the user study was conducted? Because of the complexity, I wonder whether user can judge which one is better than the other by simply looking at the layout. How was it done?
Oh, I mean that because the people we invited are students in senior, they're senior undergraduate students in architectures. I think they have some feelings of how well a layout is good regarding connectivity or some basic architectural design matrix. And also they, beside using our approach to synthesize those stuff, they also use the two simulation software to evaluate their own synthesis. And I think the scores, the costs they have are better than the real world layouts.
So the scores reported in the paper?
Yes, it's reported in our supplementary document.